realm of wastewater treatment, which took shape in the esteemed Indian Institute of Technology, Patna. Since 2021, he has obtained the esteemed position as a research scientist as HHRM Biotechnologies Private Limited. He has several publications in international repute and has obtained 2 Indian patents as well. His contributions also lies as an editorial member of several international journals and has lent his expertise as a reviewer for several international journals as well. He has held a significant role on the academic panel of an engineering college in Kolkata, affirming his dedication to academia. His academic and research community is evident through his invitations as a keynote speaker, and he has obtained several awards and distinctions to his repute and has obtained fundings from both national and international sources. His current research pursuits encompass a diverse range of disciplines, including molecular biology, toxicology, clinical research, environmental biotechnology, and the intricacies of process modeling, flow modeling, and simulation. His multifaceted expertise underscores his commitment to advancing the frontiers of scientific exploration. With these few words, may I request our revered speaker for today's seminar to deliver his lecture. Thank you all.
Thank you, ma'am, for your kind words, and thank you, everyone. Uh, I am really very happy to be a part of this presentation show today. So, I am going to start my presentation. So, this is basically my PhD work, which I am going to present. So, is my screen audible to everyone?
Yes, sir.
Is it? Okay, okay, great. Okay. So I did my PhD, as ma'am said, from NIT Agartala and delivered my defense seminar on 25th of May 2022. So I would like to present this again in front of all of you. So my topic of PhD was assessment on energy utilization from different lignocellulosic biomasses. So this is a case study, as we know that India is running, not only India, the entire world is running out of fuel, and we need to delve into alternate renewable energy sources. So this research holds an immense significance for that. So a brief introduction before I begin. As per the global estimate, the biomass production is around 150 billion tons per year, as per Faustat report in 2019. Now I believe this number has changed, I guess. Uh, but importantly, out of that 150 or whatever ton of billion tons of biomass, only 10 to 15% is harnessed for energy generation, while the remaining are being simply burned out or thrown away to get rid of those volumes. And when they are being burned out, they again create a lot of emissions, which is hampering or affecting our environmental air quality. So this is a significant number. The energy recovery potential of the biomass through the world is equivalent to 270 exajoules. So just you can imagine how gigantic volume it is. More than 30% of the energy demand in the developing countries are being made by you know biomasses. Like if we even today we can go to some villages, we will find out that they are cooking through woods, through leaves, burning leaves and all. So these are nothing but a primitive ways of utilizing biomass for energy. And in India only it is around 35,000 metric megawatt equivalent, so per annum. So these are very few statistical reports which actually indicates that yes, we biomass can be used as a very good energy feedstock. And we know that renewable energy is decreasing, so we need to put on these things. I know this topic, my research topic, is not very much oriented to microbiology, but I truly believe that the vision and mission of Arvind sir, Malini ma'am, that Microbiology Society believes no boundary, and we also believe that research has no boundary. So I think you will find my research interesting. So looking to the possible routes of biomass management, we know something could be environmentally benign process, some could be environmentally hostile process, and this box marked in yellow is neither benign nor harmful. So if we look into the
Ma'am,
hostile process,
please
yes,
put closer, please. In the gully.
hello, is anyone saying anything? Okay, so you know the environmentally benign conditions can be uh, generation of energy, whereas the environmental hostile conditions can be, as I said, that it is being often burned in field, and which causes excessive emissions and formation of smogs and all. And if we consider for the for environmentally neutral condition, then some of the biomasses are used for constructions, particularly in the hilly areas. We can see bamboo houses and all, and some it can be also used for consumption for animal feedings. So this is the overall management scenario of biomass utilization. Now, in order to generate in order to estimate the energy generation potential of a biomass, we need to take care of we need to get a few insights regarding few terminologies. So for the first one is proximate analysis, which composes of moisture content, volatile matter, ash content, and fixed carbon. So the higher the fixed carbon content of a particular biomass, the higher will be the energy potential. On the contrary, the with the increase of ash content and moisture content, the content will decrease. So same goes for the ultimate analysis, where we can define the carbon, hydrogen, oxygen, nitrogen, sulfur. So the higher the carbon amount, the higher the energy generation potential. Higher the oxygen and hydrogen, lower will be the energy generation potential. And moving on to the composition and analysis, so typically it can be categorized as lignin, hemicellulose, and cellulose. So lignin can be used for thermochemical processes like burning and all, where we can co-generate biomass. Biomass and coal can be, burnt out together to get energy. Whereas this cellulose and hemicellulose fractions can be used for microbial fermentations to gain bioalcohols or biofuels, something like that. So, what are the existing research gaps that we found out after we did a lot of literature review, and we found out that uh, typically the energy content of biomass is measured in terms of HHP, or a higher heating value, which is often known as calorific value as well. But the measurement of calorific value is it's requires lab trials, because it requires a bomb calorimeter, it requires pure oxygen flow. So and it takes a lot of time to determine the HHV of a single biomass species. You have to pelletize it and all these things. So if we can mathematically define the HHV with some components, like as I indicated earlier, with some proximate analysis, because these analyses are very easy to do as compared to the bomb calorimeter. So if we can determine these things, and with this we can compute and get the HHV of a biomass with a little bit of error contribution, that is okay. Within 5% it is statistically insignificant. So if we can do that, we can get something good. So this research have been there in the literature previously, but those research have been centric to a particular type of biomass. Say for example, some researchers have done on woody biomasses, some have done on agricultural residues like rice straw, wheat straw, and all. But a comprehensive equation for defining all the biomass is was tough. So that was our first research gap we found out. So secondly, a comprehensive analysis of different biomass categories at parallel times, like we take representative biomass from woody biomass, from processing waste, from agricultural residues, and all these things, and how, and we are trying to focus it out that which biomass category is actually suitable or the best candidate for the energy generation. So that is another important thing. The third, we found out that various pretreatment. Now we know that biomass is not a very ready-made substrate for energy generation, because it lacks a it lacks something like it has moisture content, it has ash content, okay, which are detrimental for a biomass to be a good potential candidate for, energy recovery. So which is why this pretreatment is a very important parameter. So what we did, we did different type of pretreatment at different pH, like one in acidic condition, one in neutral condition, and one in alkaline condition, to determine that how this energy recovery potential is changing, and what are the impact of different parameters like pretreatment time, pretreatment temperature. So, and finally was to optimize those pretreatment parameter. So these were the few research gaps we found out, and accordingly we set five objectives for the PhD. I will briefly describe all the five objectives during this course of time. So, first, prediction and modeling of energy recovery potential from biomass composition, like from proximate analysis and all those things. Assessment of various biomass categories for energy recovery potential, and impact of. So, this was the second objective. The third objective was to impact the various chemical treatment, as I said, acidic, basic, and neutral, and how they are improving or decreasing the energy recovery potential of a biomass class. So optimization of the pretreatment parameter and validation, key, whether the optimized condition is validated on all the biomass categories. Because being an engineering student, I always focused on the industrial aspects, like in this industrial acceptance was very important for me. I think this is very important for nowadays, because NEP have come into action, and industry academia collaboration is of great importance nowadays. So, moving on to the object one, what we did, we collected a lot of experimental data. We selected and normalized the data. We form a model. Uh, we evaluated the model through various statistical parameters, and finally compared the model that we developed with the other literature reported models. So we initially took six biomass classes like woody biomass, hidden cells, processing waste, grass, leaf and leafy waste, agro residues, and we figured out what these are the levels of their fixed carbon, volatile matter, and ash. So for woody biomass, the FC was around 13.66 to 24.47. So this is how we have defined the entire thing, because these are very important for uh, you know m- modeling for optimization. So we collected around 200 data from literature, and this is how we proceed forward. So we developed one model. So the these are the three factors. So these were the three levels, and this is how we have. So this is the basic design of experimental designing format. We use BBD or box Behenkin designing as a subset of response surface methodology. And with these design points, we did some statistical clusters. I'm not going into very details because these things are really typical. So we found out through ANOVA, or analysis of variance, which are the statistically significant terms, and this is how we generated this equation. So now this equation, so now say for example, what is the utility of this equation? So we can take any biomass of our choice. We can do a proximate analysis, because doing proximate analysis only requires a muffle furnace and nothing else. Simply with a muffle furnace, you can do the proximate composition of a biomass. Now, once you have the proximate composition, just input those FC, VM, and ash values into the into this equation. Just do this calculation, and you will get the HHV of a biomass with a maximum error percentage of 5%, which is statistically insignificant. So it is always less than 5%. It is even less than 1 or 2% that we have calculated. So this is a very good contribution to the scientific community. We did some 3D model studies to find out how this ash, fixed carbon, and volatile matter are having impact on the HHV. So we found out that this fixed carbon has a good impact, as I was telling you earlier. Whereas the moist ash and the volatile matters, the higher you have, the higher percentage of ash, the lower will be the the HHV, or the heating potential, or the calorific value. So this is what we did, and these are known as 3D plots. So we also did other validations, and so this is our results that we found out. Initially, I talked that we took six biomasses, six categories of biomasses, right? So, say for example, woody biomass. So this light portion is the predicted value, and the dark one is the experimental value. So you can see that in all the cases, the predicted and the experimental values are very close. So whatever we are predicting through our model, that equation, and whatever values we are getting through experimental validations are pretty much close enough, except for a bit deviation was there in the grass and leafy waste and agro residues. So they, in those cases where the variations were big, but still, if you found out, they are statistically insignificant because they are lying within the error bars. So these things indicated that yes, our model have good potential, and so there are around 24 to 25 models still at till that time, uh, with all these equations like mean absolute error, mean bias error, sequential error of yeah. So all these things, these are the ACP and RPT are different statistical indicators which indicates that what is the how good is your model. So we found out now this RPD value, the close to, whenever it is close to 4 or 5, it's a good parameter. So these are all literature, I'm referring to literature. This mean absolute value, mean absolute error, mean bias error, MAEMB, the lower this value, the good is the model. Same goes for ACP, sequential error in prediction. And but for RPD, the close to 4 or 5 is good. So this is what we found out. So you can see our results highlighted. So the values are very less as compared to the other values. And this is also very much close to 5, where you can see no other things, no other, are close to 5 except this one. So comparatively or collaboratively, we found out that our model has very good potential, and it can be used for any biomass categories, irrespective of all these things. Say for example, Ebeling and Jenkins, their paper was focused on woody biomass. So the model they proposed are totally for woody biomass. They cannot be applied for agricultural residues. They cannot be applied for leafy biomasses. But now, some researchers might have considered one or two parameters, like they are considered for woody and agricultural residues. But a comprehensive model for all the biomass categories we presented for the first time. Now, after this modeling and validation, we move to the second objective, where we assessed various biomass categories for energy potential. Now, what we did in this case, we took four biomass categories over here and a representative from them for parallel evaluation. So for woody biomass, we took bamboo stem, because since I was in Tripura and Northeast during my PhD, so whatever biomasses we chose were very much prevalent to Northeast, because this case study was somewhere related to the Northeastern India only. So we found out pineapple is, again, that Queen pineapple is very famous in Tripura. So pineapple crown we took as a processing waste. Rice straw we took as agricultural residues, and kugun grass, or it's a type of grass. So that we took as an example of for the leafy biomass, fresh leafy biomass. So the scientific name of kugun grass is Imperata cylindrica. As far as I remember, I am not a botany student, so I may be wrong. But as far as I remember, it was Imperata cylindrica. So, and for reference, we took diesel as a standard reference. Now, what we did for parallel evaluation, we put diesel into the diesel generator, and parallelly, we also had a biomass based generator where we were putting this biomass fuels. Now, before putting the biomass was evaluated through calorific value, through thermochemical analysis, through proximate analysis, as well as composition analysis, and we put them in the energy recovery in hybrid system. So after energy, there will be three things. For means once it is put into the generator, it will generate three things. Definitely, it will generate energy. So this is over here. It will create some emissions. So these are the emissions like COx, NOx, SOx, HC, PM. PM means particulate matter. Okay, okay, and finally an ash or residue. So with those things we put into and this emission part, we know that energy is good. Okay, we can use that for our needs. Ash is also good because it can be used for dumping. Sometimes ash have different, potential. It can be used as biofertilizers. It can be used for water purification like adsorption and all. So these two things are okay. Energy and ash is fine, but what about these emissions? So for the emissions, are they okay? Means we are generating energy, that is fine, but in that, with that process, it should not be like that ki we are polluting our environment. So we quantified that emissions through LCA based sustainability analysis or life cycle analysis. We also did an economic analysis, and this is how we concluded this portion. So these are the standard protocols that has been approved, that has been used throughout the study. M's, moisture content, volatile matter, ultimate, then higher heating value, composition analysis, sustainability analysis, bulk density, all these things. So we yeah, I was right, it was Imperata cylindrica. So we systematically classified those biomass. So woody and non-woody biomass. Okay, we did their lignin, cellulose, hemicellulose, and extractables. So we found out good amount of extractables, lignin and cellulose was present in all the biomass specimen. uh, we did the proximate composition also. We found out ki everyone have fixed carbon more than 15%, which is good. But yes, bamboo has more fixed carbon and very less ash content. So it is only 2% ash content, but whereas in rice straw, in all these things, the ash contents were a bit higher. Same goes for moisture content, it was around 10% for all the biomasses. We did carbon, hydrogen and oxygen evaluation. So with the ultimate analysis, so we found out they contain good quantity of carbon from 35 to 45%. Oxygen and hydrogen was also in substantial amount. We also did HHV, or we tried to generate the energy potential. I mean, estimate the energy potential. We found out bamboo has the highest energy potential. We found out bulk density, or in short, density. So bamboo was the highest dense material. Uh, then we did a thermogravimetric mass loss profile through TG and DTG, and we found out key three distinct phases of uh, degradation was obtained. So in the first stage, were mostly moisture evolved around 100 degrees centigrade. You can see over here, this axis is temperature. So up to three, from 300 to 400, we found another peak, which indicates that it can be volatiles. Okay, which are actually now living. And finally, this zone is for ash. So we found out three distinct zone, which was very much correlated with our experimental thought process, whatever we thought. Okay, so next we put those things in those generators. We had that particular generator at our NIT. We put those things along with battery cells was also there, and we found out the specific energy output. So it was around 1.1 for bamboo, one. So this value was at for the different biomasses. For diesel, it was found out to be 2.6. This is the specific energy output, that is kilowatt hour per kg. So if you burn per kg of biomass or per liter of diesel, so this is how much kilowatt hour energy you will be getting. So it clearly indicates that since we know diesel is a very good fuel, so diesel has got very high energy, that is okay. But you can see the biomasses are also not bad. So like bamboo has 1.1, it is good enough, around 40 to 45% of the diesel. But these are creating less environmental hazards that we will learn in the due course of time. This one I am skipping, it's a bit okay. So now finally, so we found out ki chalo, it's okay, the biomasses have good potential for energy recovery, they can be used up. Fine, but what about the emissions that they are creating? So this was the next question. Are they okay? Are they in the acceptable limit? For that, in order to quantify that, we had to do a life cycle analysis. So this was very new terminology. So life cycle analysis is something like it's known as cradle to grave analysis. Like whenever it can be done for any product. Say for example, we we are talking about a mobile phone manufacturer. So whatever inputs it is taking to create a mobile phone, okay, whatever is a process to manufacture the phone, and whatever are the processes that when we are dumping it after using, how it is being recycled. So during all these phases, how much energy emissions they are creating, how much SOx, how much SOx, COx, NOx, particulate matter, hydrocarbons they are generating. So this is actually the motive of life cycle analysis. So we found out ki you can just see the numbers. So these are thought provoking. So for diesel, this CO2 is around 1.23 kg per kilowatt hour, whereas for biomass they are in the power of 10 to the minus 4. So you can imagine how things are different for everything, for dioxide, carbon monoxide, particulates matter, SOx, NOx, particulate matter, ash. Everything was very, you know, lower as compared to conventional fossil fuel. But yes, for ash, all the biomass generated a lot of ash, whereas diesel actually have no ash. I mean, literally not no ash content, and definitely the energy was also pretty much higher as compared to the other biomasses. But yes, emissions, it is absolutely fine, which is why we call them carbon neutral fuels, because they don't emit such so much of things. So next we found out this global warming potential. So you can see this is the global warming potential, this is acidification potential. Like when we are generating energy from biomasses, the global warming potential is so less, you can see. But see, for diesel, it is so high. For acidification potential, they are so less. For diesel, it is so high. So you can see for everything, the conventional fossil fuels are very much environmentally, threatening option. So switching to green energy is definitely the need of an hour. Now we did a scoring metric analysis to find out ki which out of these four biomass, which biomass which is the best candidate. So with a different scoring metric that I'm not getting into very details, we did a lot of analysis to find out ki this rice straw is good candidate based on the emission. Remember, this is totally based on the emissions, because being an environmentally conscious citizen, I had always focused my research towards environment, because some great soul had said that environment is all that we have in common. If we have environment, we can do anything. Then after that we move on to objective 3. Now we have selected that rice straw is a good candidate now. But if we look into the energy is very less for rice straw as compared to diesel. So now the immediate next objective was to increase the energy, to bring it very close to coal or diesel. So for that, what we were doing, we started pretreatment, because we know that pretreatment is a good option. So what is pretreatment? It is basically reacting with some agents, chemicals, and these chemicals selectively remove few of the fractions of the biomass. Like if you treat with acid, it will selectively remove the lignin content. If you are treating with alkali, it will selectively remove the cellulosic and hemicellulosic content. So what we took biomass. As I said in the through the last slide, biomass was good, the best candidate. We treated them for 3 hours at three different conditions. This one is acidic, this one is NaOH alkaline condition, and this one is hot water, that is neutral condition. So post treatment, we did physical analysis, chemical analysis, and economical analysis. Now we need to find out that which treatment condition is good for improving the energy. So now we did the composition analysis. So UT means untreated, HW means hot water, A means acid 10%, acid 20%, acid 30%. Similarly, B 10%, base 10%, base 20%, base 30%. So these were the specimen codes. We found out that lignin was around 19%, but with the increase in acid treatment, the lignin was increasing. You can see from 22 it went to 27, then 31. But with the increase in severity of the alkali treatment, the lignin was getting down. Okay, so as I said that whenever we are treating it with alkali, so the lignin portion will be removed, and whenever we are treating with acid, the hemicellulosic portion will be and the cellulosic portion will be removed. So same thing you can see with the increase in acid treatment, this cellulosic portion was getting down, and with the increase in alkali treatment, the it was getting up. We did the moisture for proximate composition also and found out that yes, the moisture is also increasing, but significantly this fixed carbon was increasing with acid treatment. You can see from 24 to 26, 27, whereas it was decreasing with alkali treatment. For 10% it was 6, for 20% it was 5, for 30% it was 4. Okay, for hot water it is equivalent. So now these shaded data are means they are statistically significant. Okay, so we did statistical analysis as well and found out that it is statistically significant. Okay, so again we found out that acid treatment is good. In the last slide we found out that it is improving the lignin content, which means in thermochemical process we will get more energy, because thermochemical processes totally rely on the lignin content of the biomass. And here also we found out that fixed carbon is also supporting the same observation. Fixed carbon is increasing uh, with acid pretreatment. Same goes for the elemental carbon as well. You can see it is from 35.18 to 35.255393. So it has improved. Whereas the hydrogen has decreased, oxygen has decreased with acid pretreatment. So this means it is become a carbon rich fuel with less moisture. So this is a Van Crevelen plot. So the basic thing, sir, is that we plot HC versus OC in this thing. In x-axis we put OC, whereas in y-axis we put HC. And whenever we are plotting a point, the more closer to the origin, the more is their energy recovery potential. So we found out that the acid pretreated biomasses are very much close to the origin. You can see, whereas the alkaline protein pretreatment biomass are very much away from the origin. So this indicates that acid pretreatment has improved the energy recovery potential of the biomasses as compared to the neutral condition and alkaline condition. So now all our data are indicating that treatment is good. We should go for acid treatment for improving the energy recovery potential. So finally, we did the HHV and bulk density. So you can easily see that yes, the energy has improved significantly with the increase in acid concentration, but the energy has decreased for alkali. The density have also increased significantly, because density means higher energy. For alkali, it has decreased. Okay, now we did a detailed cost analysis. Okay, because whenever we are as an engineer, it was always challenging to provide a economically sustainable solution for us, because if it is not economically sustainable, then it is of no use of pretreatment. So we did a lot of calculations, back end calculations, that I'm not going to details. So we found out he acid 30% is giving you a profit of around 10%. So it is not only increasing the energy, but also giving you economically beneficial things. But for energy, for alkali treatment, you are facing a loss. See, you can see a minus over there. So economically also acid treatment is good. We found out. So this is what we did, and we concluded from this objective that yes, this thing is okay. We should do pretreatment with acid to improve the energy. Now the immediate next question or was key, at what parameter we should pre-treat, at what time, at what temperature, what particle size. So there was a lot of question. So we figure out through optimization by using box Behenken designing, which is a subset of response surface methodology, and it we address that problem through the fourth objective. So what we did, we took rice straw, we treated it at different time, temperature, acid concentration, SLR or solid is to liquor ratio, and particle size. We optimized and developed a nonlinear model. Now see, with increasing treatment time, like 1 2 3 4 5 hours, it was increasing. So we took that. For acid concentration 10 20 30 40 50, it was increasing and then slow down. For temperature 80 100 120, up to 120 it rose, then it straight away. But with solid and liquid ratio and particle size, you can see the effect is very flat. So we took these three factors like time, temperature, and acid concentration. Okay, and we took time up to 3 hours because after 3 hours there was no effect. After 30% there was no effect. So acid concentration up to 30%, and temperature up to 120 degrees centigrade because after that there was no effect. Again, we use the same design of experiment lab format, and through the statistical analysis, we found out this equation. Okay, so these are all very I'm not getting into details of these things. We found out with increasing time and temperature and acid concentration, the HAG was increasing, which means the energy potential was improving. So after this numerical optimization, we found out that at 3 hours, 120-degree pretreatment temperature and 29.5% acid, we are getting the maximum increase in HHV. So it is around 22.64%. So if we treated these things, a biomass for 3 hours at 120 degrees centigrade with acid concentration 29.5%, then the energy will be increased to 22.64%. So that is a very notable thing. We could improve the energy by around one fifth. So 20% is around one fifth. So this was a significant achievement because most of the times industrial optimization results in 12, 13, 15%. So getting a value more than 20% is really good. Now the immediate next objective was ki chalo, we have done this optimization for biomass rice straw. Is this biomass rice straw, whatever we have done for rice straw, like we defined a pretreatment condition over here, 3 hour, 120 degree, 29, will it be same for all the other biomass categories, or this is very much particular for these biomass categories? Because now we again need to find a generalized solution. You cannot just say these things to a unknown person. For woody biomass you put these, for this biomass you put this, because these farmers and all, they were unaware of these things. You have to put them in an integrated solution. Whatever is irrespective of the biomass class, you put this thing, and you will get a improvement of around one fifth. So this is what we can suggest them. So the next question was to find out, yes, is it okay with other biomass classes, or we have to do some modulations. So with that, we framed our final objective, where we did the validation of the optimized chemical pretreatment for various other biomass categories that we have evaluated in our PhD. So this optimized model we took from last objective, we validated across different biomass categories, and we took the impact, how it improved. So this was nonlinear model. Okay, that for rice straw, we tried using it for the other biomass classes. So this was for A was for bamboo, B was for cocoon grass, and C was for pineapple ground. Now you can see the experimental predicted data are not very much close to each other. So yeah, they are close. They are not too far away, but they are not too close also. Because if you see the R square value, it's around zero point 0.7, zero point 0.8. So something around zero point 0.9, 0.95 would have been much better. So we modulated the equations. So we refined the cofactors and found out and retuned the models. Okay. So retuned the models, and then we did all the statistical analysis. We did the three-dimensional plots and found out key for all the cases. After tuning, the time was around 3 hours for everyone. Temperature was 120 degree for everyone, and the acid concentration for bamboo was around 28.99. Again, same for 28.99 for cocoon grass, but for pineapple it was around 29.18. So if we focus it ki chalo, let's put like 29% of acid, the time and temperature is same for all, whereas 29% of acid concentration is good fitting for all the biomass categories. So this is what we proposed ki this is the optimized condition. So 3 hour, 120 degrees centigrade and around 29%. So what we did the experimental value and the predicted value, and we found all the deviations are below 1%. For this one, it is around 1.818%, but for the other classes, they're 0 point less than 1%. So this indicated that whatever refinement we have done even in our model was up to the mark, was good, because the deviation between predicted value and experimental value is very less. Now this is a very complicated and thing that we have done. So I mean, things are simple but put in a complex manner to fit into one slide. So this BSUT, so bamboo stem, untreated bamboo stem optimized. So now we took bamboo stem normally, and we also took it from the bamboo stem after treating in optimized condition. Same for cocoon grass UT, cocoon grass O, PCUT, PCO, pineapple ground untreated, pineapple ground optimized, RS, rice straw UT, and rice straw optimized. Now we found out, see, the lignin content of all the biomasses have improved after acid treatment. See, it for woody it was 28%, then it straight away moved to 40%. From 16 for cocoon grass, it went to 23%. From 4% to 6% for pineapple crown. For rice straw, 19% to 22%. So lignin has improved. Now moving on to the fixed carbon, see ash content had decreased from 2% to 1.2%, 6% to 5.9. Okay, so ash is getting down. Fixed carbon is moving up, which is again a good indication. 18 to 29% for bamboo. For cocoon grass, 15 to 23%. For woody biomass, I mean pineapple crown, 17 to 23%, 14 to 24%. So you can see this increment like 59% up, 46% up, 47% up. Elemental ratios have decreased, which means they are moving towards the origin, which means they are becoming more good fuel. Okay, and finally, this bulk density is improving, and definitely the HHV has also improved 25%, 14%, 18%, 22%. We did the thermogravimetric analysis, and again we saw three clear zones. Okay, for pretreated as well as non-pretreated biomasses. We did other different ratios like fuel ratio, combustibility index, flammability index, combustion index, volatile ignitability, fuel value index. Now these are all the parameters that are being checked for a coal when they are being used in a for burning and giving us energy. So after pretreatment, we found out that all the biomasses have moved towards the this value have better went better. So from 5.25 it went to 5.54. So you can see it has improved for all the biomasses. I am not going into very details, but yes, for all the biomasses it improved, all the pretreatment parameters, all these conditions. An economic analysis was also done, so we got good economic benefit: 14% for bamboo, for coconut grass 5%, 6%. For pineapple, ground rice straw, it was around 11%. So economically, it was also good. And now we did another scoring matrix based on fuel ratio, FVI, fuel value index, combustibility index, process economics, and we defined a pretreatment impact score. The higher, the better. So considering all these things, we found out that rice straw has got the best pretreatment value. So it is coming around 13 out of 16. So overall, our research concluded that rice straw is a very good thing, substrate for energy generation. If we do some, uh, modifications, slight pretreatment modifications, it can revamp significantly and become something like coal. So we can co-generate in electricity. Like with coal, we can put these things, biomass pretreated, and get energy. We have done as a simulation in our lab. We got good results, so maybe we are looking for further expansion. So, what are the summary and conclusions? I would like to wrap up now. So, initially, we developed a non-linear correlation model to propose and predict the calorific value of different biomass categories. So, not for one biomass, for all different biomass categories with minimum error contribution. So, the error contribution is also less. In the second objective, we compared assessment of different biomass categories and present along with the determination of environmental burdens. So we not only evaluated different biomass categories together, but also we saw what is their environmental burdens through life cycle analysis, and also put a perspective on the overall process economics. How is the process economics going? Whether it is profit making or loss making. So we found out profit making. Next, we found out key pretreatment. What is the impact of pretreatment? Which pretreatment zone we should do, in acidic, in basic, or in neutral condition? That we found out. Okay. So, and we then defined a pretreatment condition that around 3%, around 120 3 hour, around 120 degrees centigrade, and around 30% acid concentration, most of the energy improvement will happen. So a future scope definitely lies, because we have done optimization. So more advanced forms of optimizations are present nowadays. So we can do that. Uh, and definitely we need to experiment in real time scenario, because these are all lab oriented scenarios. I know that when things will go into commercialization, a lot of other factors will also come that we need to evaluate and take care of. So these were the publications that we did. So we published around 12 to 15 articles during my course of times, and thankful to my supervisor for his constructive efforts. And definitely I would like to thank my parents and all. And finally, I would like to thank MSI for giving this opportunity, for me to showcase my research in front of this esteemed research community. So, with this, I would like to wrap up, and I would be happy if you have any questions. Thank you.
Yes, the forum is open for discussion. Please, the participants, you can take part.
Uh, yeah, after printing, how you have? So, I have some few questions over here.
Yes, you can
So,
go ahead and answer them.
yeah. So, Professor Prakash, thank you, Professor Prakash, for your kind words. Which is the best biomass to obtain max calorific value, and why? So Professor Prakash have asked me which is the best biomass to obtain max calorific value. So first, to answer your question, I would answer, if we are only considering calorific value, not these emissions and all, then woody biomass are the best candidates, because they have the highest lignin content. The harder the biomass, the higher will be the lignin content. So this is the general thumb rule. So if you're only considering calorific value, go for the woody biomass. But if you are going for, since lignin are complex compounds and whenever burned produces a lot of emissions, but again those emissions are very much less as compared to fossil fuels. So how do we determine global warming potential from different fuels? So as I said, sir, we can put these things in a fabricated generator, and we can use some software, simulation software like Gabi. With Gabi, which is a product of ThinkSafe Corporation, Germany, you can actually determine the different life cycle indicators, like, as I said, global warming, acidification potentials. They have different input and output criteria. Once you have put those things, you can get to know key, yeah, which biomass is actually how much contributing towards the global warming. Sir, how you measure pretreatment after HHV after pretreatment? Okay, so we took the biomass, we put it in particular mass is to liquor ratio. Say for example, if it is 1 is to 10, so we will take 10 gram of biomass in 100 ml of liquor, or in acid, 30% acid. Then we will put it in a constant temperature. Through temperature monitoring, these things are there, oven. You put it, you keep it for 3 hour, 2 hour, whatever is your duration. So then strain it, put the acid away. Okay, take the biomass things, air dry it or oven dry it, you can also use. And this is ready for HHV. So again, you have to, now what we did, we measured 2 times, one through the model that we defined, and one through experiment through bomb calorimeter. So what was the method used for lignin content determination? It is as per AFA, I guess, APHA. They have different organization have different things. So basically, lignin concentration can be determined by alkali precipitation method. So you can get a lot of literature reports in this. In even in my PPT also, there was a standard protocol mentioned. So thank you, Thapa sir. Bharat ji, lignin percent increasing after treatment. Is it good? Yes, it is good because for now it is a very good question, because if we're considering the thermochemical pathway, like the burning of coal for energy, for this thing, increase of lignin percentage is good, because whenever we are burning something, the lignin content is burning. Okay, but remember, if you're trying to generate bioalcohol like bioethanol and all, for that we have a different scenario. We need to remove the lignin fraction, because lignin being so much big molecules, often the microbes cannot degrade it. So they generate ethanol by degrading the cellulosic fraction. So if it has lignin contents within it, so it will hamper the fermentation procedure. So yes, the for thermochemical process, higher the lignin content, better is the yield. But for cellulosic thing, it's totally opposite. How this biomass was used for fuel generation? So alone biomass was not used, as I said. Battery was there, photovoltaic cells were there, PV DG battery. Okay, so PV DG means diesel generator, and a part of the thing was used as biomass. Now you can see blended fuels. So 20% or 10% of bioethanol is blended with 80% petrol. It's not like no need to for petrol. Petrol will be one of the major constituent, but we can reduce the consumption by adding 20% bioethanol. Same for this well as well. But lignin content should become low after treatment, right? Because that's the main aim of the treatment. One of the focusing protection. But yes, now I think Rithi Vashi asked me a question. As I said, for my thing, I was focusing on thermochemical process. So my main agenda was to preserve the lignin. Now, if you are going for a biochemical pathway, where you are producing bioalcohol, then your vision should be different. It should be 180-degree opposite. You should remove the lignin straight away, so that you have the core cellulosic materials, and when you are going for fermentation, it will generate bioethanol. So for bioethanol, lignin is a hindrance. We should remove lignin. But for thermochemical process, lignin is good. Cellulosic is the hindrance. You should remove cellulose. So which is why partial fragment fractionation is there. Okay, you cannot totally remove the lignin, you cannot totally remove the cellulose because they have been interlinked. But yes, partially 20%, 30%, 40% removal can be done. Which are the acids used? And okay, we use sulfur, basically strong acids. See, people have different opinion in with different acids. Some of them says that ki chalo, if we use weak acid also we can get good results. But what we have found out, strong acids can do better. And what we have done, say for example, we have 30%, we have taken 30% acid, so we have pre-treated it and strained the biomasses and take that liquor. When we again back treated that, we found out ki the strength was coming around 27-28%. So only 2 to 3% has been consumed. But on the contrary, if you are putting 2 to 3% of acid, it will consume only 0.2, 0.4%. Because proportionately that would also decrease. So strong acid has better performance. As per our thing, we use sulfuric acid. Initially, we did this study with a lot of acids: sulfuric, HCl, HNO3, acetic acid, weak acids, a lot of things. But we got best results in sulfuric acid. Some people have also reported good results with HCl. But with an HNO3, mm, things are not good. Okay, Riddhi. Okay, Riddhi, all the best for your yeah, for your PhD, I guess. So if you have any other queries, I think you can always connect with me. I will be happy to help you. I will see, Professor Prakash. Yes, commercially available technologies are what we are working. People are working in India, but again, till date, few of the companies have taken good initiatives. Okay, they are moving towards net zero emission, where they are considering key whatever things we are throwing away, we should be reusing it for our internal energy generation purposes. So yes, people are working on it, but not very much prevalent. And regarding the cost economics, whatever we have found out, it is very much beneficial. And apart from that also, we are helping it, uh, helping the community, because these volumes are big. Whenever agriculture is happening, they raises a lot of rice straw, wheat straw, paddy straw, whatever. So at after some time, the farmers have no other option rather than burning it in the open field. So if we can prevent that and deviate towards energy, so environmental degradation, you must have noticed smog formation in Punjab and all during the winters. So they can be prevented, and definitely it is beneficial as per our study. Third is, can biohydrogen used as a biofuel? Yes, biohydrogen definitely can be used as a biofuel. Nowadays, MFCs are we a lot of people are working with MFC. So apart from, and one more interesting thing is that biohydrogen a can be is actually a waste product whenever we are purify. I mean, treating water, so we can treat water as well as get biohydrogen from that. So that is a very good option. Biohydrogen research has significantly evolved nowadays. A lot of people are working on the biohydrogen production, and particularly, this MFC or microbial fuel cell are very good reservoirs for biohydrogen production. Email ID. Okay, I will be sharing my email ID. So I have shared my email ID with you. I am also sharing my contact details. So if you have any queries, Riddhi, you may connect with me. So I would be happy if anyone have any other question. It was really nice interacting with all of you.
Sir, can you hear me, Dr. Rupak?
Yes, yes, sir. I
Yeah,
can hear
actually,
you.
I am actually have some little bit network issue. This Jatropa, no, is used.
Yeah,
How is the
Jatropha.
potential? Now Jatropa also they are not using much for a biodiesel production.
Yeah,
What is your
Jatropha. So
view?
Jatropha is basically, it's a very potential thing, for biodiesel production, and a lot of people have
Okay.
used. So a lot of studies are there actually with Jatropha. So
Mm-hmm.
water hyacinth and all these things, a lot of studies are there. Jatropha is very much potential. It is good. So you can regarding this, for biodiesel production and all. Uh,
Mm-hmm.
for me, this fresh leafy biomass holds better, potential. Like Jatropha can be good. I mean, the origin should be fresh leafy biomass. Then it can be used
What
better.
about the buttery cookers?
Pardon, sir?
Some buttery cookers also is used algal for biodiesel
Alki,
production.
yes, yes. Alki is definitely, it's an upgraded version,
Mm-hmm.
because it's third generation, so it's good. Alki is definitely good because they are very rich in lipids. Mm. So, and they are easy to cultivate. They are easy to
Exactly.
use. So, in fact, one of my colleague was, who is now assistant professor in one university. So we were doing PhD together. We were just working in different labs. So he was working with algae. So he got very good results with this algae things, and also prototyped one patent. So yeah, it has got immense potential. Algae is very good, too good. I should say it's better than biomass.
You have not focused much on the fermentation part, fermentation downstream processing in your presentation.
Sir, my I have not focused because my route was not biochemical. My route was thermochemical. So downstream was never an issue for me. Whatever things are generating, like ash, we can straight away
Okay.
deposit in agricultural fields. Downstream processing is very much important for those who are working in biochemical pathways, like as you said, in this biohydrogen production. So over there, definitely you need those things. But in thermochemical pathway, you are only generating emissions. You cannot take control of that. It will anyway emit. Whatever is remaining are the ashes. Energy that we are utilizing, that is good for us. Ashes, we can go for water treatment, like adsorption and all, or we can, these are also used as good fertilizers. So I have not focused on downstream as a lot.
Last question is from your experience. Now, as you also mentioned that in Punjab or in Delhi, the smoke problem, no, because of burning this wheat straw. So, ligno means solubilizes this sugar cane or wheat or paddy also, because paddy is mostly grown in south, and then no, very less utilized. So, how do you feel? How economical is to convert into the bioenergy, or at least converting them in the usable form, either rice straw or the
Sir,
wheat or
see,
the sugar cane.
whatever, yeah, it's a very good question. Whatever, as per my experience, what I will say that bioalcohol generation is a good thing. I am not demoralizing it. But
Hmm.
what is happening whenever we are going for bioalcohol production, we require a sterile lab, sterile culture, because whenever we are doing this culture, so a lot of contamination might occur. So whenever for this bioenergy, okay,
Mm-hmm.
I think thermochemical path is the better, because it is a very fast process. You do it, you pretreat it within 1 day, pretreatment is over. Just co-feed it with coal, you will get good results. At least you can save 18 to 20% of your economic budget. But if you are moving to the biochemical path, you are producing bioalcohol, that is fine. But it is taking a long time. You need to maintain pure culture. Sometimes they are economically challengeable because you are using biological instruments like laminar airflow,
Yes.
incubator for several days. So your electric consumption is increasing. So as per my suggestion, my knowledge, because I had done a lot of literature review initially. After that only I have choose this thermochemical pathway, because this is very much rough and tough. You can do it. So I would
What is the
suggest
what?
thermochemical.
Yeah, what is the your end product you claim?
End product is energy, sir. Energy
In which
and energy and ash.
in which form? Which form of the energy? Calories.
Just like coke, I mean, whenever we are burning coal, we are getting energy. Same thing, along with
Okay.
coal, just add 20%. Initially we
Hmm.
were using 100% coal. Now what we can do, we can
Okay.
take
Okay. Okay.
70% or 60% coal or 80% coal and remaining with this pretreated biomass. So
Wonderful.
co-generated.
Wonderful.
So you will get, even coal have also got a good ash content. So this biomass will
Mm-hmm.
also have a good ash content. So you can just take away those biomass, those ashes, and you can use it for other applications. It has got again a good applications for fertilizers, for land filling purposes, for water purification. This ash can be used.
But any substance when we burn, usually, no, its value
Hmm.
decreases, right? Suppose you have a good quality wood, we
Yeah,
burn it.
yeah, yeah.
You will,
Value
yeah,
will
you will
decrease.
get it. Yeah, you will
I
get
know
a ash.
that is why I'm telling ki use only 10 to 15%, 20%, not
Okay,
50,
okay,
60%.
okay, okay.
Because at that optimized level, the
Hmm.
value won't decrease much. Because you
Exactly.
are also saving the cost of the coal, na?
Yeah.
So you are saving 1 rupee, say for example, and you are spending 20 paisa. So ultimately you are getting 80 paisa benefit. It's like ATP synthesis. You are producing 4 ATPs, consuming 2 ATPs, but still you are having 2 ATPs left. So you are in the profit side.
Yeah, yeah, looks quite convincing. Thank you. Thank you very much.
Thank you, Professor.
Hello, sir. There
Hi,
is,
hi, doc.
hello, sir. Your presentation is very informative. Thank you very much for that one. So,
Thank you.
again, my small query is, are you speaking about the algae? So, is algae is people are using for the thermochemical treatment processes or not?
Sir, could you please repeat your question
Is
once again?
algae is
Algae,
using for the thermochemical, what is you are generating heat, yes, by using thermo.
chemical and biochemical. Hmm.
Yes, yes. You are saying, yes, I know, by using through biological process, we are using algae for the two generation of different products. But what about thermo process?
Sir, basically, microalgae are typically used for lipid. They are harnessed. The lipid, they have good amount of lipid content within them. So whatever we are doing, we are harnessing the lipid content. And with those lipid content, through transesterification, with uses of catalyst, we are actually producing, biodiesel. So that biodiesel, so if we consider technically, it's a consortia of thermochemical and biochemical process. Okay, it's not totally biochemical, not totally thermochemical. uh, that has got good potential, but again, you with biodiesel you can use it as a transportation fuel. See, we can save energy from different fields. Not only electricity is only consumption, we are also consuming diesel. So nowadays these blended fuels are coming in. It has already come in India, where you can see 20% ethanol blended, 10% ethanol blended. So these things are coming from these lipids. So it's not a thermochemical process directly. It's a biochemical process through which we are actually we are actually producing biodiesel, bioalcohol.
Thank you, sir.
Okay, Karan, you have a question. Which is the best method for biohydrogen production, from agro waste or from microalgae? I guess from agro waste is better from as compared to microalgae. I am not sure. This is just my presumption. I think agro waste would be a better candidate because microalgae have a good lipid content which can be harnessed for bioalcohol production, not for hydrogen. But still, I need to check out with this. Sir, energy that is released from treated biomass can be also used for production. Yes, yes. Not instead of coal. It can be used as a co-feed with coal. As I said, we can apply around 10 to 20% of those treated biomass with 80% coal. So it will eventually reduce the coal consumption. So now today we are talking about 10-20%. Who knows? After 5 years or 10 years, we can totally rely on this. So researchers are going on, and I think we will be successful one day, because anyway the prediction is telling that around 50 to 60 years we will be having access to coal and petroleum. After that, these things will exhaust. So we need to take care of other processes. So, any other question from anyone? You might type it or just ask me. So, I guess. So, thank you everyone for your questions. Thank you, Malini
Yes,
ma'am. Over to you.
thanks a lot. The interactive session actually we planned from MBSI for such things so that like people come in contact with different areas of work and like they can just um, make use of the opportunity to fulfill their interest in working in the field. So thanks a lot for your lot of great time, and we look forward for further communication. Definitely, we will be in touch with you. So, and
Thank you,
thank you
ma'am.
all the participants for being with us on this Sunday morning. So, once again, the next week we meet for the next session.
Thank you. Thank you everyone for your time. Have a nice day.
Thank you.